Let's just get right into it. Welcome, 7/29/2020, last lecture day of the class. Let's just go over some things real quick. The quiz, or basically the last exam, you guys did okay on. Usually you want to look at that normal curve, and you can see our normal curve has high B, low A as its average, which is pretty good. So you guys did decently well. There's only one question that you guys just were confused on, but it was a fair question, so not much we can do about that. That was the last one where it asked about endothermic versus will it feel cold or will it feel hot? And endothermics will feel cold. They will not feel hot. Exo is hot. Endo is cold. So you guys are good. You guys are doing great. Almost done. You have this quiz tonight, and then you have the test tomorrow. The chapter 25 test is just it's just the one chapter, so it's only 25 25 questions. So should be easy. We're doing the nuclear chem stuff, so there's not a lot of math. It's mostly just alpha, beta, gamma decay, that kind of thing. So you guys should be pretty good and quick on it. As far as like reading about it and whatnot, I'll put up the links. I don't know why the links didn't post, but we'll put those back up and make sure those guys are there for you guys to use and study from and whatnot. So let's just go ahead and get started talking about radioactive decay and nuclear chemistry. So for the beginning part of the year, we talked about chemistry, and for the most part, it was really just the electrons doing most everything. The protons are important because they identify the nucleus and tell it what properties it's going to have in terms of it being a gold or a mercury or a platinum or whatever. That's going to be different protons. But for the most part, the protons are just kind of sitting in there, just kind of hanging out in the nucleus, and the neutrons are in there as well. So the question is, what is the chemistry of the nucleus? Like, what are they going to do? Like, the chemistry of the electrons is amazing. There's so much different stuff out there. They inorganically combine, they organically combine, they have all kinds of cool different reactions. There's light production, all this kind of stuff. So what's going on with the nucleus? And so that's what we're going to look at here in chapter 25, is we're going to look at what do protons and neutrons do in the nucleus. And the answer is not that much. Basically 5 things that we're going to talk about. 3 most important, which we say alpha, beta, gamma, and then some things that humans have figured out called nuclear fission and nuclear fusion. So let's get right into it. So the nucleus of an atom, as you guys know, is the protons and the neutrons, and that the different isotopes of an atom are atoms that have the same number of protons, but they have different numbers of neutrons. So protons and neutrons have the name called nucleons, which some people use, but it's one of those old terms, not used that often. So what is going on in the nucleus? So when it comes to fundamental forces in the universe, you have gravity, and you have electromagnetism, and you have the strong and the weak nuclear forces. So what is the strong force? The strong force is what holds a nucleus together, the attraction between the protons and the neutrons, and of those particles to each other. So strong force is extremely powerful. However, the protons are still positive. So they are still pushing on each other. So what happens after you go past um, hydrogen? You gotta have neutrons inside of your nucleus to stabilize the strong force fighting against the repulsion of the protons. And so there are good ratios of protons to neutrons, and there are some ratios that just don't work very well. And so what this causes is nuclear instability. So if we look at, for instance, the first couple atoms, hydrogen, for instance, we know that there are three isotopes of hydrogen that we've talked about in the past. And hydrogen 1, hydrogen 2, and hydrogen 3. This one's called hydrogen. This one's called deuterium. And this one is called tritium. If we looked at their nucleus, well, that one would be one proton. That guy would be one proton. That guy would be one proton. But this guy would have no neutrons, and this guy would have one neutron, and this guy would have two neutrons. And so when it comes to the nuclear stability of this, we're getting less and less stable as we go across these three isotopes. And the reason for it is we're adding a lot of strong force, and there's not a lot of proton repulsion to balance that strong force. And so these neutrons just don't need to be here, and you get what we call unstable nuclei that want to fall apart. And then if we just go on to the very next atom, we have helium. Helium likes to be helium-4, but it can also be helium-3. You could rarely get helium-5 and helium-2, but we're going to ignore those for now. And inside this helium, we have two protons. For it to be helium, it needs to have two protons. But in helium-4, we have two neutrons, and in helium-3, we only have one. So in the case of these two different isotopes, the nuclear stability is going to be based off of what is the better ratio. And when it comes to helium, helium-4 is the better ratio. And we know this because when you look on the planet, you're looking at like 99% of the helium on the planet being helium-4. Helium-3 is so unstable that it will begin to fall apart. And so this is what we call radioactive decay. When you have an unstable nuclei, because the proton-neutron ratio is just not favorable. And so as we keep adding protons, we have to keep adding neutrons. And that whole, in the beginning, you can see that it's kind of one for one. Like the most stable nucleus of helium is helium-4, so that's 2 and 2. But when you go to look at lithium, lithium is a little weird. Helium is positive 3 protons, and sometimes it has 6, but sometimes it also has 7 as its mass. That's 3 and 4 neutrons, respectively. But you will notice in the first bit of the periodic table, the average atomic masses are pretty much basically like twice as big as the atomic number. And that's because at the beginning, a ratio of about 1 to 1, 1 to 1.1 is pretty good for protons to neutrons. As we get higher and higher in the periodic table, we start to see that ratio start to go up to 1, 1.4, 1.5, to the point where eventually we hit element number 83 on the periodic table, which is just no longer stable. There are no stable isotopes after bismuth. So if we go to the periodic table, your guys' periodic table, you guys have that. If not, I'll post another one because I don't know why it deleted the last class, so you guys can't look at it anymore. think we used this one. No. It's not the one I clicked on, but okay. Boop. Science notes. 118 elements. Yay. All right, so if you look at the beginning part of the periodic table, you'll notice that it's 5 and it's 10 and it's 6 and it's 12 and it's 7 and it's 14. But then when we start getting down here, we have 29, and then double of 29 would be what? 58. So, but this isn't 58, it's 63. And so you can start to see that the ratio of protons and neutrons starts to start becoming 1.1, 1.2. And when we get down here to gold, gold is element number 79. And instead of that being 158, it's 196. So we're almost up to the 1.5 to 1 ratio as neutrons to protons. And so once we hit bismuth right here, every single atom after bismuth does not have stable isotopes. Every single one of them is radioactive. Every single one of them will undergo radioactive decay. So when we look down here, actinium, thorium, protactinium, uranium, they have average atomic masses nowadays. But again, all of these things will be radioactive because they will decay. Uranium-238, for instance, even though it does have one stable isotope in terms of that it sticks around for a few billion years, it still is radioactive. It still will fall apart. The radium will eventually degrade into lower elements. And under a long enough timeline, you will see that if you were to go to the universe that was, if you were to visit the universe a trillion years from now, a lot of areas would probably have elements up until bismuth, and then that would be it. Unless there was more star production and things like that, eventually they will decay into bismuth and lower, and then that will be it. That's the end of that. So yeah, that is nuclear decay. It is the unstable nuclei falling apart. And the reason they're doing this is they're trying to readjust their ratio. They're trying to make it so that their proton-neutron ratio is better so that they can exist as lower energy. So how do they do this? Well, they actually don't do it in a lot of different ways. They really kind of only have a few tricks up their sleeve. And the vast majority of those tricks are alpha and beta decay. Other than that, and then positron is a type of beta decay, and electron capture is a variation of beta decay. And then, of course, there's gamma. So really, they just kind of do these two kind of things, and they switch it up very little with these gamma, positron, and electron capture reactions. So what are the types of radioactive decay? And then where did they come from? So just a little background on radioactive decay. We'll get into each one, but they are discovered by a guy named Henry Becquerel. Henry Becquerel was the guy who discovered radioactivity. He put some uranium salt ores that he was studying in a drawer and went on vacation. And then inside the drawer was a bunch of photo paper. If you guys remember how photos worked back in the day, they had to develop them. And so he left the rocks in there thinking no big deal. Came back from vacation, got his rocks out so he could go back to doing research, and noticed that the rocks had basically taken pictures of themselves on the photo paper. So he figured that there must be something radiating from the rocks, some sort of light, because that's how that photo paper worked. It interacted with light. Then it was Madame Curie and her husband who were working on, mostly Madame Curie, who were working on what exactly was this radiation coming from the rocks. And so she was able to describe it. She described it as radioactivity, and her big claim to fame was isolating various atoms that were in the uranium ores, and then she was the one who named most of the radioactive decays. Most of the radioactive elements that were in that, what we call uranium salt. Then Rutherford, who was interested in describing how atoms worked, decided to study radioactivity as well, and he was able to split the different types of radiation into the three types: a positive type, alpha, a negative type, beta, and a neutral type, which is called gamma. So that's where those alpha, beta, gamma terms come in. And then there are just 1,000 other scientists that did amazing work on nuclear chemistry around the turn of the century. So that is how we've discovered radioactivity. So what the heck is alpha decay? So say, for instance, you're a nucleus. Clear canvas. You're a nucleus of, I think, carbon 13. Yeah, we'll do carbon 13. So normally carbon is carbon 12. And carbon 12 is 6 protons. But it's also 6 neutrons, and they're kind of in there doing their thing, and they're stabilizing the nucleus. And carbon 12 is considered to be trillions of years in stability, meaning the nucleus of a carbon 12 atom is so stable that it will stick around for trillions of years. But the very next atom or isotope is carbon 13. And the only difference between carbon 12 and carbon 13 is that instead of 6 neutrons, it has 7. It has a 7. And the instability of carbon 13 is so great that it will want to fall apart into, it'll undergo alpha decay in only a few number of hours or weeks. It is pretty fast to decay. So what exactly happens? So what happens is what we call a nuclear reaction. The nucleus is going to want to try and stabilize itself. So what it's going to do is it's going to undergo alpha decay. And what is alpha? Alpha is when the nucleus that is unstable decides it's going to spit out 2 protons and 2 neutrons. This is a helium nucleus. It has the atomic mass of 4, and it has 2 on there as its number of protons. So we have 6 down here. And it has a positive 2 charge. Now, some people will write the charge, some people won't. It's not really that big of a deal if you don't write the charge. So that means then that 2 protons and 2 neutrons, and this is called, have left, and this is called the alpha particle. Alpha is like a little fish-looking thing. So the alpha particle is a helium nucleus. That means that we have a nucleus left over. And so in a nuclear equation, just like a chemical equation, we want to balance everything so that it's about the same on both sides in terms of nucleons. And we had 6 nucleons, and there are 2 here. So that means we now have 4 nucleons left. There were 13 total nucleons, and 4 of them left. So that means we have 13 minus 4 left over here. So that is going to be 9 nucleons. Okay. And if we look at the periodic table, element number 4 is beryllium, and its average atomic mass is pretty close to 9. And that's because beryllium is very stable at being beryllium 9. So what we have is our 4 protons, and we used to have 7 over here, neutrons, and 2 of them left, so we're left with 5. And that is our nice stable nuclei. This here is called the daughter particle. This right here is called the parent. So the parent will then decay into the alpha particle and the daughter particle, and this is what we call alpha decay. In the case of carbon-12 is super stable, but when carbon is in the form of a gas like carbon dioxide or methane, it will float up into the upper atmosphere and it can be bombarded by neutrons from the solar wind. And when it gets hit with these neutrons from the solar wind, sometimes it can grab a neutron and it will form the isotope carbon-13. And because of the stability of the beryllium and helium, this is just a better way for them to rearrange themselves. So the way I like to think about it is in terms of like going to an amusement park. You've gone to an amusement park with this big group of 13 people, but as soon as you get there, you going off and hanging out with your 3 best friends is probably going to happen, and you're probably going to leave this other group over to do their own thing. And maybe they're super big into hanging out with each other, so the group will split up. Or like, say for instance, it's you and your 13 family members, and like you and your brothers and sisters go off, and then the adults go off and do their own thing. And that's kind of the idea. There's a group of people that are more comfortable with each other, and they try and split up. And the whole point of this is to try and stabilize these nuclei. So that's alpha decay. So in the case of our little PowerPoint here, it tells us some examples. Radium-226, polonium-218, thorium-230. So how do you do these? Well, you go radium, and you're going to look at the periodic table for radium. Radium is down here, and it's number 88 on the periodic table, and it's Ra. So if you wanted to write a nuclear decay for radium, it's 88. And then you look at which particular radium they're talking about. In this case, they're talking about the isotope 226. So this one is radium-226. Then you draw a line, and if it says do the alpha decay, remember that this is the alpha particle, so we're going to draw the alpha particle, and you can write the charge or not, it's up to you. And now we're going to predict the daughter particle. And for that, it's really simple. You just do, you're trying to make them even on both sides. So 226 on this side, 4 on this side. So that means this thing needs to be 222. 88 on this side, 2 on this side. So this needs to be 86. And then you just go to your periodic table, find number 86 on the periodic table, which is radon, and then write the symbol for radon. And that's it. That's all you have to do there for alpha decay to predict what's going to happen. You just subtract 4 and 2 from the top and the bottom, and then look it up on the periodic table. That's what I meant by, this is, high level concepts, but it's actually not that difficult in practice. Another example here is the radioactive decay of polonium-218. So polonium is PO. It is 218. Let's go to the periodic table. Where is polonium? 84. So we go 84. And this is alpha decay. So we're going to draw the alpha particle. You can draw the charge or not, it doesn't matter. And now again, same thing. 218, there's 4 over here. So then to add some number plus 4 is 218. So that's going to be 214. And then 84, here's 2. So some number plus 2 is 84. So then 82. And then we go to the periodic table, find element number 82. And this is lead. And so that is alpha decay. It's pretty simple to do. So then what is the other major decay? So there's a nice basic setup of the reaction. You have some element, and then the daughter particle would be the A value minus 4 and the Z value minus 2, and then you'll have the alpha particle. You'll notice they didn't write the charge there. Okay. Beta decay is the other major type of decay. And in beta decay, what happens is that one of the neutrons decides to switch to becoming a proton. And when it does this, it spits out a high energy particle that happens to be negative. So it basically is an electron. But the reason why we call it an electron, but we also like to call it the beta particle, is because of the fact that of how much energy it's going to have when it leaves that nucleus is way more than an electron normally has. And so the comparison is like if you hit an atom with some X-rays and that electron gets knocked out of the atom, you ionize that atom, that electron is going to have about as much energy as if you were to take a bullet and put it in a slingshot and hit it with the slingshot. But if you were to take a electron and have it be emitted out of the nucleus in beta decay, then we're talking about like railgun levels of energy where it's not just being even shot out of a gun. This is being propelled at even faster than a gun can repel it. That's how fast these particles are coming out of there. So let's take a look at then our little drawing here. And again, we're going to use carbon because carbon has another isotope, carbon-14, and carbon-14 will undergo beta decay. So in carbon-14, we have our 6 protons again, and we have 8 neutrons. Okay. And so this is an unstable isotope because if this were undergoing beta decay, it would result in the more stable configuration of 14 still being the same number of nucleons, but now instead of 6 protons, we'll have 7 protons. And so this is beta decay. Beta decay has the symbol of either beta with a 0 and a -1 here, or it has the symbol E with a negative and a 0 -1 here. You can see both ways. Your textbook tends to use both. It depends on what you're particularly trying to emphasize, if you're trying to emphasize the electron or if you're trying to just say that it's beta decay. So in this case, this is our beta particle. And you'll notice that it is got 0 up here and a -1. And the reason for that is, again, we're drawing these on here to make our drawing show the average atomic mass or whatever. So there's our beta particle. You'll notice it's not red or green because it's not a proton or a neutron. But we're still going to do the same thing. Our nucleons are not going to change because you can see that it says no change to the nucleons. But what it says here is that it's a -1. So remember that they got to add up to this number. So 0 and 14 add up to 14. But some number -1 has to equal 6. So instead of subtracting, we're actually going to be adding. And this is nitrogen. And nitrogen in this case has now, instead of the 6 protons, one of the neutrons became a proton. So now we have 7 protons and we have 7 neutrons. So in the beta decay, we have the one of the neutrons becomes a proton, and when it does this, it spits out a beta particle. You'll notice that it says the daughter particle is Z+1 rather than Z-2 in the previous example, and that the A's stay the same. Now, it depends on the particular beta and how you look at it in your book or versus the internet. Sometimes they'll mention the production of a neutrino or an antineutrino, but in the case of our level of knowledge, you guys don't need to worry about neutrinos and all that kind of stuff. But if you want to be a nuclear physicist, then you might want to talk about neutrinos. So the half-life, or the ability for this to fall apart, is much more stable than carbon-13, but it's still unstable, and we're looking at about 5,600 years for this to want to start to fall apart into the nitrogen. But we can use this for what we call carbon dating, where we can look at a living organism that has died. If it has died, it is no longer eating, and therefore no longer is absorbing new carbon-14. So all the carbon-14 that it had in its body will begin to decay. And we can monitor the ratio between the carbon and the nitrogen to find out how long ago it died, which is pretty cool. All right. So then we now have gamma, and gamma is what we call gamma rays. There aren't particles, they're high energy light. And in the case of gamma, gamma tends to be a side product of other radioactive decays. So like alpha and beta can be so energetic of a change that sometimes that energy has to be emitted as a gamma ray. Or sometimes the nucleus is so kind of unstable in the ratio of protons to neutrons that it can try and just spit out that gamma ray on its own. And the symbol gamma has the symbol 00, and then of course the Greek letter for gamma. So that is gamma decay. A good example of gamma decay you may have heard of is cobalt-60. Cobalt-60, cobalt is number 27 on the periodic table. And the cobalt-60 is so energetic that sometimes it will just produce the gamma radiation trying to stabilize its nucleus, the cobalt-61 in particular. But you could also have gamma radiation released as a result of a nuclear process. Like for instance, uranium-235, 92, if this were to undergo alpha decay, then we would result in the 231, 90 thorium being produced, but it would also produce a gamma ray. And again, you won't have to be able to predict when that happens because that's based off of like internal electron voltage energy numbers that we're just not going to bother with. And even if you're an AP Chem, they don't even mention that stuff. So, but if you want to be a nuclear physicist, you can join the Navy and they will teach you all about nuclear power plants and put you on a nuclear submarine. And yeah, you can be a nuclear physicist through the Navy if you want. Pretty cool. Otherwise, it's, you know, college and lots and lots and lots of work and getting security clearances to work on nuclear stuff, things like that. I just wanted to briefly talk about positron emission and electron capture real quick, just so you guys know that there are alternatives, but they just are very rare. So for instance, we have what's called positron emission. Well, it turns out when it comes to matter, there's also this stuff called antimatter. And so when you're talking about making an electron can be negative. It can be a negative excitation in the electron field, but you can also have a positive excitation in the electron field, and that's called a positron. And so in the case of beta decay, if we make a negative electron, then we call that beta. But if we make a positive electron called a positron, then we call that positron emission. You'll notice it makes different types of neutrinos and antineutrinos. But you can actually see this happen, and you may have actually seen it on a very, very dark night. If you've got your eyes closed because you're about to go to sleep and you saw a tiny little blue flash in your eye, this was some of the carbon in your eye. If you had very rarely some amount of carbon-10, one of those carbons might have undergone positron emission. And as soon as that positron was made, if there was an electron around, they will instantly annihilate each other, releasing the energy, and your body will actually be able to detect it as a blue light, which is pretty cool. So if you've seen or heard about Chernobyl, which we'll talk about in a second, one of the things the first responders to that accident described was all of the tiny blue lights in their eyes. And that's because a lot of the beta decay that was occurring, but there was also positron emission occurring, and they were seeing the little flashes of light as the positrons destroyed electrons in their eyes. So if you are in a situation where you think there's radioactivity and you start to see blue lights in your eyes, you have probably already been exposed to a deadly amount of radiation. But if you do start to see those, you want to get the heck out of there. And then you have the rare occurrence, which is called electron capture, which is a nucleus can grab an electron and then a proton can become a neutron, so kind of the opposite of beta, and it will then kind of reverse. And then, of course, it spits out energy as a neutrino. But again, you guys don't need to write these guys out. Then we can have what's called a decay series, where you can chain down, but you guys won't have to do decay series. But basically, if you have a super big element, like say you have the element 118, it will start to decay over time into eventually a stable isotope until it gets down to something like lead or bismuth. And then it's stable and happy. So alpha, beta, gamma. So let's talk about their power, their strength in terms of energy and penetration power. So when it comes to, say we have a block here and inside of it we have some sort of radioactive material, and the radioactive material is able to spit out alpha particles, and it's able to spit out beta particles, and it's able to spit out gamma particles. Well, if our detector is back here, okay, and we shoot at this, the detector, all three of them will hit. But if we put up a piece of paper, just a piece of paper, thin regular piece of paper, the alpha particles will bounce off. So alpha cannot penetrate paper, but beta can and gamma can. Then if we put up just a piece of cardboard, then the beta will bounce off. But here's the crazy difference between power of alpha, beta, and gamma. Because alpha and beta are actually particles, they have interactions with matter. But gamma is high energy light. So to block the gamma, you're going to need 6 inches of lead. And then the gamma will be absorbed by the block. So in terms of the amount of energy that's inside that particle, alpha particles are stopped easily by paper or even the dead skin cells you have on your body. Beta can penetrate things like your clothes, but if you have like a thick sweater on, then the beta particles will be absorbed by the sweater. But if there's gamma, you need yourself a lead box, or you need to get under like 6 feet of dirt to be able to try and protect yourself from the gamma radiation. And this is why there was a craze for a very long time to build fallout shelters. And you'll notice if your house has a fallout shelter, that it is at least 6 feet underground. And the idea behind that is that if there is a nuclear explosion, then the gamma rays will not be able to get to you because they will be absorbed by the 6 feet of dirt. But when it comes to radiation, are they still all bad for you? And the answer is yes. They are all what we call ionizing radiation. They can all strip your atoms of their electrons. And so because of their high energy, they can ionize. And if you ionize your atoms in your cell walls or in your DNA, then it will destroy them. So in the case of the helium nucleus that has a +2 charge, that is extremely damaging to tissues because that helium will steal those 2 electrons from the very first thing it touches. Alpha particles are actually the leading cause of lung cancer because in your house, you might have radon, and the radon might be producing helium alpha particles. And because you're in your house, you're breathing these in. And so they're getting in and they're hitting your lung tissue inside your lungs, and they can begin to cause lung cancer. As time has gone on, smoking has become the leading cause of lung cancer, but before smoking, or if your area has reduced its amount of smoking, then radon is still the #1 cause of lung cancer. And you can't really do anything about it because it's just coming out of the dirt. So you can ventilate your house, but say, for instance, like your basement, you lock it up and there's no vents in there, and you go on vacation for a very long time and you come back in, that door down there, there may have been radon buildup. You might want to open windows before you go down there for any long amount of time so that you avoid the exposure to the alpha particles. This is also one of the reasons why California has no basement rule, because of earthquakes mostly, but also because in California there's a large amount of radon activity in the soil, so no basements. And it comes to the beta particles, they are high energy electrons. So electrons need somewhere to go and they're super high energy. So if they bump into something else, they can ionize them. They can either force they force themselves onto atoms. They can also knock electrons off of atoms. And so they are strong ionizing radiation. And so beta particles are also very dangerous. And this is why when you are wearing protective equipment, it needs to be kind of thick to block out the beta particles. And then, of course, gamma radiation is going to go all the way straight through you, and it can impart energy along the way, but its big damage is to your DNA. It will destroy the DNA molecules. Your cells will then no longer have their blueprints. And so when that cell that's now damaged by the high energy gamma decides it wants to split itself into 2 new cells through mitosis, it doesn't have good DNA, and these cells will be unviable. And so once you get hit with enough gamma radiation, your cells, just the ones you have, are the ones you're going to have. And as they die, your body starts to shut down. It is a terrible, terrible way to die. Also, it doesn't feel like much at first until you're gone. So that is alpha, beta, gamma decay. Pretty simple. So just a real quick idea about half-life. So when it comes to the stability of the nucleus, we could talk about in terms of the amount of electron volts that are available in the nucleus. But another way to look at it is just the amount of time it takes for the isotope to decay. And so what a half-life is the amount of time it takes for a sample to decay into half its original size. So if we have a 100-gram sample of a radioactive isotope, how long does it take for that 100 grams to become 50? That's called a half-life. Then another half-life will occur when that 50 becomes 25, and when that 25 becomes 12 and a half, and when that 12 and a half becomes 6.25, and so on and so forth. So this is the concept of half-life. And so basically, the bigger the half-life, the longer you are going to be stable. So I don't want you guys to have to do any of this math with the half-lives, with the leftover original amount, all that kind of stuff. I just want you guys to know about the different examples of radioactive isotope half-lives and how they show the stability of the nucleus. So let's go ahead and look at those carbon isotopes again, and you can see the different stabilities in the nucleus. This is going to be greater than 1 trillion. We don't actually know what the half-life of a carbon-12 atom is. It is so long. We've not observed the decay of carbon-12 yet, as far as we know. I mean, it might have happened in the last few years, but basically, it is about forever. But like I said, carbon-13 is going to be in the terms of years, and then carbon-14 is in the terms of about 5,600 years. Okay, so as you can see, the stability, this guy is the most stable, and this guy is the second, and this guy is definitely the third. Okay. So that is the way that we can use half-life as an understanding for terms of the stability of that nuclei. So a good example of this, as we're going to talk about nuclear weapons here in a second, uranium-238 is the vast majority of the uranium in the soil in Earth. 92 uranium. It has a half-life of about 1.8 billion years. Okay. Its other isotope that you can find in the Earth's soil is uranium-235, which only has a few thousand years. So I think it's like 1,800 years or 1,400. I don't know off the top of my head. But either way, as you can see, the stability of the uranium-238 is far greater than the stability of the uranium-235. And that's why if you were to go get a sample of uranium, you would find out that most of the time, this is about 99% of the uranium you're going to find, and this is only about 1%. Now, it depends on your area and your source of uranium, but sometimes it can be as much as like 3%. It really depends on your particular sample of uranium. So as you can see, because of the uranium-238 having such a longer half-life, there's way more of it on our planet. Our planet is very old, 4.5 billion years old, and so most of the uranium-235 has decayed, and only samples of uranium-235 that we're finding right now are from other larger elements decaying that are inside the uranium salts. So pretty cool. So a question you might be asked is like, okay, a sample is 300 grams and it is now 75 grams. And if it takes 200 years for a 1/2 life, then how long has it been since this sample started to decay? And so you'll just, the easiest way to do this is just to start cutting your original sample in half until you reach the number. So 300, we divide that in 2, we get 150. So we have 1/2 life, and then 150 divided by 2 equals 75. So that gives us another half-life. So this is 2 half-lives. So if we have 2 half-lives and they're 200 years, that gives us a total of 400 years. That's it. That's all there is to it. If you look up the half-life equation, you'll have a fancy equation with, algebra 2 level stuff in there. Don't worry about that. You're not going to be asked to do that. You're asked simple questions like, if there were 2 half-lives that occurred and the half-life is 4,000 years, then what's the total amount of time that has occurred? So it's pretty simple. So that's the idea behind half-life. The shorter your half-life, the more unstable and the more radioactive that isotope is going to be. One of the things that Madame Curie was famous for, remember we said isolating elements, she was able to isolate polonium and radon and also radium. And what she found was that the half-life of the radon was hours. And so one of the more unstable nuclei that was produced from her uranium salts, and probably one of the more dangerous aspects of it. So that's the vast majority of your stuff you need to know for the test. But I just want to talk real quickly about nuclear weapons and nuclear power plants and also stars. If it will load. It might not load. All right. So alpha, beta, gamma are the natural ways that things decay. But sometimes in very radical situations, alpha, beta, gamma is not enough of an energy change for that nucleus to try and stabilize itself. And so what can occur is what we call nuclear fission, where the nucleus actually falls apart. Now, nuclear fission is considered to be natural in some cases, but the vast majority of nuclear fission that we as humans do is artificial. We're going to turn a regular, normally pretty stable isotope into an extremely unstable isotope by hitting it with some sort of neutrons or protons or what have you, and this will cause our nucleus to become so unstable that it will fall apart. Humans have then also found special nuclear isotopes that can cause what we call a chain reaction, where you start the reaction with like one neutron, and then when the thing falls apart, it spits out other neutrons, which can then continue the chain. So let's see how this works. So again, we're going to go to these cool PhET simulations. You guys can check them out if you want. We want chemistry, but it's not our page anymore, which is okay. Chemistry. Might be in physics now. Moving stuff around. There we go. There's alpha decay. There's beta decay, so you guys can play with those. There we go. This one right here. All right, this took a little bit to load last time, so we'll see how it goes. So while we're waiting for that, nuclear fission uses a nuclei that when it gets one more neutron or one more proton, becomes extremely unstable. And a great example of this is uranium-235. If we were to bombard uranium-235 with a neutron, it will go to uranium-236. It is this uranium-236 that is extremely unstable. And so what will happen is if we bombard our uranium-235, we make uranium-236, and alpha and beta decay are not enough. And so the nucleus actually splits into barium and krypton. So here's a good example. This one is showing the cesium and the rubidium, the ones we used in when we first started playing with this would result in mostly barium and krypton. And so the reason why this is an important, what we call fissile reaction, is you'll notice that it took a neutron to start the reaction, but when this reaction decays, you'll notice one neutron goes in and 3 neutrons come out. You can also have 2 neutrons come out in the case of the barium krypton. Sometimes you only produce 2 neutrons. Sometimes you produce 3 neutrons. It depends upon the energy that is going to be removed by the system. But either way, what this can do is give us what we call a nuclear chain reaction. So if you see here in this simulation, we only have one uranium nuclei. But if we enrich the uranium to basically like 90 something percent uranium 235 and about 15% uranium 238, we can now get what's called a chain reaction. We shoot the one neutron, and then those decaying uranium 236 molecules, or sorry, atoms, begin to break down the other uranium 235 atoms, thus releasing a huge amount of energy. This is called nuclear fission, and it is what occurs in a nuclear weapon. In a nuclear weapon, we're going to want to get that chain reaction to happen all at once, so that way all of that energy is released at once. You'll notice that we have uranium-239 here, and so those uranium-239 molecules can be used by allowing them to undergo beta decay, and when they undergo beta decay, they'll produce plutonium-239, which is also a fissile material. If we type in plutonium-239, we will also get a fission reaction. In this case, in our fissile uranium-239, it can produce some fissile products. So in this case, the uranium produces a nearby product that can then generate more 239. And then, of course, you can get that to start to undergo beta decay, which generates more, which then falls apart. So here's kind of a more elaborate version of it, where you get the eventual production of the plutonium-239 down here. See that? So that is another fissile product. So this is what occurs in a nuclear weapon. You're going to get yourself some uranium from the ground. You're going to then split it up using what's called centrifuges. So I am a chemistry teacher, so they usually ignore my searches, but obviously, you know, get yourself on a list looking this stuff up. But basically what we have here is we have our sample of uranium, and what they can do is they can gasify it. And when they gasify it, the heavier uranium-235 sinks where the uranium-238 sinks, and the uranium-235 floats a little bit taller, and so they can start to suck off the lighter uranium-235 and get rid of what we call the depleted uranium, which is uranium-238 and uranium-239. So once you've increased your percentage of uranium-235, you can then undergo a chain reaction when introducing the uranium to the neutrons. So if we reduce, like say in a power plant, we reduce this to sometimes only as much as 20%, but usually it's less than that. And we increase this up to 80%, you'll notice that the chain reaction takes a lot more to get started, if it will get started at all, because it kind of don't like the positions of these. There we go. And it just missed it. So you can see you can control the reaction a lot better with a lower concentration of the uranium-235. In nuclear weapons, you're looking at getting as much as you possibly can, somewhere above 90% of the sample would be uranium-235. And when that happens, the chain reaction is very easy to sustain. This is discovered in 1939. The first chain reaction is done by Enrico Fermi underneath the tennis courts at the University of Chicago in 1939. And then the United States starts working on the Manhattan Project to make the first nuclear weapon. And it's not until 1945 that they're able to make the first nuclear weapon. First nuclear weapon they make is called the Gadget, or otherwise called Trinity, or the Trinity test. And that is the very first nuclear weapon to ever go off. Happens in 1945, June. The Manhattan Project is headed by two major scientists. One is a military general, General Groves, and then Robert Oppenheimer is the lead physicist on the project. And there are many sites in the Manhattan Project, but the main one is in Los Alamos, New Mexico. So yeah, it kind of looked like this. It was a big, what we call compression bomb, which I'll show you in a second. And basically, it was a big giant core of uranium and plutonium that would get crushed. And when it was crushed, it would then give off the neutrons needed to start the chain reaction. So it was just on the top of a tower. So it would be up in here, and then they would make it go off. And a very famous pictures of it, because they used time-lapse photography, showed this kind of like scrubbing bubbles kind of image of it going off. And of course, you can watch declassified videos of it, and I put a link to a video of that, the different types of nuclear weapons. So once that was done, then they used two different bombs. You had Fat Man bomb and you had Little Boy. Fat Man is what we call a compression bomb, and the same thing as the Trinity test. And basically, in the Fat Man bomb, you have a core of uranium and plutonium, and then you have some what we call beryllium igniter. And basically, what happens when you crush this beryllium, it gives off neutrons. And so the plutonium and the uranium get crushed by explosives, and this causes the beryllium to send a huge number of neutrons into the plutonium and uranium cores, and the chain reaction starts. To have the correct number or the correct percentage, and to have enough to actually cause enough energy to be released, you have to have what's called critical mass. And so their nuclear weapons have like a limit to how small you can make them. Otherwise, they will not undergo fission. The other bomb is called Little Boy, and Little Boy is what's called a barrel bomb. And this one was untested when we used it. A barrel bomb works like this, where you have a target that is your uranium target or your plutonium target, and you have a uranium bullet. And what happens is that you detonate your explosives here, then the bullet travels down the barrel and is slammed into the other half of the critical mass. And then the slamming of these two together cause the compression that you need to cause the reaction, the chain reaction to start. So here's kind of a different angle looking at it, where you kind of have like a plunger, and then you have like a big mass of uranium. At the time, and this is one of the reasons why the United States becomes so technology advanced when it comes to military after World War II is beginning of the project. This bomb was considered impossible because there was no metals that could handle the amount of pressures and temperatures that would be going on in this reaction. And so through alloy science, they were able to design better metals to be able to make the barrel bomb work at all. The compression bomb was their idea they came up with because they didn't think they could make the barrel bomb work. But through lots and lots of research into metal alloys, they were able to discover alloys that they could generate to be able to contain this and actually make it work. But again, when it came down to dropping this bomb was untested. And so that was the two types of nuclear weapons that came first. Then we figured out how to use this for nuclear power plants. Basically, we have fuel cells. So right here are a bunch of fuel cells. And what we have here are neutron absorbers. So what we can do is we can control our reaction by moving this slide in between our fuel rods. And so if we start our reaction, you'll notice that the reaction started here, but the neutrons bumped into this blue thing and they didn't keep going. So now we can control this by continuously firing neutrons to try and get the reaction to start chaining, and it will start to produce power. But if our power starts to be a little too great, we can start closing it down. And then you'll notice that we are producing energy, and we can then, we're going to start losing energy, so we can start speeding it up again. And so this is what we're doing when we're dealing with nuclear power plants. We're controlling the chain reaction. This is very difficult to do with uranium-235, and it's what has led us to many, many nuclear disasters. There are other isotopes, though, that would be able to produce plenty of energy, but would have a very hard time melting down. And we'll talk about what that means in a second. But basically, uranium-235 and the uranium salts, because of the extreme fissile nature of uranium, it can produce so much energy that it starts to melt those salts. If the fuel rods are melted, then we can't put our regulatory control rods in between them. And the reaction runs away because the rods melted down. And so this is why we call that nuclear meltdown. So you can see nuclear meltdown occur if we just remove the fuel rods and we fire some neutrons here, like we're going to start our plant, and there's some sort of cause that causes our things to fail here, like in the case of Chernobyl or 3 Mile Island or in Fukushima. And you'll notice that the temperature starts to get so high that we can then begin to melt our fuel rods. And this is what we call a nuclear meltdown. So a better alternative nuclear fuel that we could start using would be thorium. Thorium has such a high melting point that it physically can't melt down, but also if it gets hot, it becomes a bad fissile material because the neutrons, that it just can't absorb them anymore. And so instead of them becoming absorbed and then causing fission, they become absorbed, or they just pass right through, and the reaction just kind of tends to slow down. So they're a little bit harder to control, but they can't undergo nuclear explosions or nuclear fallout. So that's the idea behind a nuclear reactor. You have the fusion reaction taking place now, or fission reaction taking place, and you're trying to control it. So then humans discovered nuclear fusion. And so what occurs with nuclear fusion is we have, I was right on this. We have atoms that are going to combine together. In the case of this, we have our deuterium, and it's going to come together with some tritium. And these two nuclei will then fuse into helium, but it will also produce a neutron. Because you notice 2 and 3 is 5, not 4. So it produces helium, but then it also produces a neutron. So humans figured out nuclear fusion, and what they decided to do was to use the nuclear fusion as a source of neutrons in nuclear weapons. But what they also found out was that the actual process of fusion resulted in huge amounts of energy. So we had figured out and made what we call hydrogen bombs. And they're called hydrogen bombs because they use deuterium and tritium, and sometimes they use lithium and tritium and things like that. So in the case of fusion, my computer's barely handling this. So fusion. In the case of a nuclear fusion bomb, what we have is we have ourselves a compression bomb here, and that compression bomb goes off just like we would have in a normal nuclear weapon. And what it does is it causes the fusion reaction to occur. And when the fusion reaction occurs, it produces way more energy and way more neutrons. And so any of that wasted uranium and plutonium will 100% undergo fission and fusion, and we get way more energy out of the bombs than we do in the case of a normal atomic bomb. When it comes to atomic bombs, we tend to measure them in terms of kilotons. And when it got to atomic bombs, we had to start measuring them in megatons. So if you want to play with it, you can type in nuke it, and this is idioms. We don't want that. There we go. So nuke it will give you a nuke map, and you can go to this website and you can type in any city you want to nuke, and you can pick the nuke you want to drop on it, and you can start to see the different types of devastation that can be caused by the different types of nukes. So you guys are over here in Claremont. So to give you guys perspective, we can take our little guy here, we can move it on over here, and plop it on the Claremont there. And if we want to use the original Trinity bomb, the gadget, you can hit detonate, and it will show you the kind of devastation that will occur. And it tells you what each thing does. Basically, if you're inside the yellow circle, you're inside the fireball. And then if you're in the gray circle, that's all like just the instant death all the way out to here. And then, of course, radiation and whatnot. And so the Trinity test is what we call a 20 kiloton bomb. Fat Man was also a 20 kiloton bomb, a little slightly different. And so it had a little bit larger of a blast damage. And then, of course, if we compare that to the very first hydrogen bomb, which was called Ivy Mike, as you can see, they are a completely different amount of devastation between the hydrogen and the regular atomic bombs. So yeah, that is difference between fission and fusion. Fission occurs in stars. So and basically when a star is formed, you get just hydrogen, and the hydrogen will combine together and you'll start making helium, and then you start making beryllium, and then you can start eventually making larger and larger atoms. Unfortunately, though, for stars, that all nuclear fission doesn't release energy. Once you have made iron, the nuclear fusion reaction requires more energy than it gives out. And so the moment a star has started to use up its fuel to the point where it's starting to fuse things into iron, this star is going to die, and it's going to undergo either supernova or nova, depending on the size of the star. And it is this last nova or supernova explosion that then gives us every single element after iron on the periodic table. So there you go. I'll post a couple more videos here in the module. I don't know why they got deleted, but I'll post them again. And then if you want to play with that NuKit, I'll put that on there so you can see the different nuclear reactions. But that's it for today. If you have any questions, you can feel free to ask them and I'll answer your questions. But that is everything you need to know about radioactive decay, half-lives, fission versus fusion, nuclear weapons, nuclear power plants, so on and so forth.